Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out with your Unit 2-1 homework. We're going to chat about numbers 3, 4, 6, and 7. So number 3 says something about a locomotive pulling a train. So we might start with a quick picture, just like all of these problems. It doesn't have to be a great picture. I'm going to let this be my train. There's my locomotive. Yeah, great picture, right? We better write train on it so people know what that is. Okay, and it says something like the locomotive exerts a force of, mine says 7.9 times 10 to the 5th newtons on the train. Yours will likely say something else, and you should put that in the picture. So the locomotive is applying a force this way on the train. Where that force vector goes in the picture is kind of up to you. Forces have what's called a line of action. It can go anywhere along this line. So you can put it over here like it's pulling, or over here like it's pushing, or in the middle. What you can't do is put it up here or down here. And again, I'll talk more about lines of action later. I'm going to go ahead and put this force right here. So again, this was a number given in the problem. Now, there are other forces acting on the train. There's gravitational forces, and the trains are being supported by the tracks. I'm going to leave those off because those are vertical forces, and this question is all about what's happening in this direction right here. So, whoops, let's call this the plus x direction. And then it's just a matter of applying Newton's second law, which is sum of all forces equals mass times acceleration. And this is the only force acting, and the mass is given, so that should be enough to get that problem done. There's not much left. So moving on. Okay, number 4. It says a 22 caliber rifle has a .47 meter long barrel. When fired, the bullet, which the mass is given, mine says 2.5 grams, but yours will say something else, accelerates from rest and exits at a certain speed. Mine says 370 meters per second. So as usual, you might want to start this with a picture. And the problem is about the bullet, which starts out here at rest. So we might say something like initial velocity of 0. And let's say here's my barrel. This will be like the inside of the barrel. And when the bullet's being fired, it's being pushed by gases that are back here expanding. We can use a motion diagram, remember, to represent the bullet, the snapshots in time. Click, 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 click. You know, my digital camera. Is the final velocity given? Yes, it is. All right, so the V final is given. The length of the barrel is also given. So there's really two types of physics you need to do here, right? There's what I'm going to call the motion study here, and then Newton's second law. Now, by motion study, that's the type of physics we have in this class been studying the entire time. Start with a velocity graph of the bullet. I don't want to get this too done, it's your problem, but right, again, velocity against time. And at t equals 0, the bullet's here, not moving yet. Sometime later here, that we don't know, the bullet has exited at a speed or a velocity given in the problem. So now, this is where people always get hung up. I don't know what the time is, so they just stop. You assign a name to it, we'll just call it t, and move on. So this point, t, v final, is a point on this graph. T, v final. So, and again, on these velocity graphs, this, whoops, in red here, this, darn it, one more time, there we go, red. There is your time, your delta t. And then in green, that's your delta v. And we'll go ahead and make a constant acceleration assumption. Now, turns out that's probably not true in a case like this. But again, you know, the whole idea behind mathematical modeling is to make certain simplifying assumptions that will allow us to move on. Now, this distance right here, this is our change in velocity. This was given in the problem. The time not given, and the acceleration we don't have either. Use area. This area right here, you've got, you know, 1/2 red times green, if you will, is equal to the length of the barrel. You can solve that for t. Then the slope, which is the acceleration, is green over red here, right? Delta v over delta t. Then you can come over here to apply Newton's second law. These gases are pushing, they're applying a force in this direction on that bullet. And by Newton's second law, that force is equal to mass of the bullet times acceleration of the bullet. So that's plenty for number 4. Let's chat about number 6. Take me a moment here, I gotta scroll down and see it. Let's see, an 8 kilogram object, so right away they're giving you a mass. Write it down. Mine says 8 kilograms, yours is probably a different value. And they've given an acceleration. Mine says 2.7 meter per second squared, you've got a different value. 6 is just a standard Newton's second law question. When they say, what is the net force? Just write out Newton's second law, net force equals mass times acceleration. These values are given. This problem is pretty close to trivial. 7. So number 7, it's talking about a train with a mass given. You are also given a force on it. So from these two things in Newton's second law, find the acceleration of the train. And then part B, it says, how long will it take to increase the speed of the train to 78 kilometers per hour? So that's a question about motion, and I always recommend a velocity graph. Assuming the train starts from rest at t equals 0, not moving. Sometime later, that we don't know, the train needs to be going a certain velocity. I'll call it a v final. This was given in the problem. Assume constant acceleration, and that acceleration is equal to the slope of this line. And that should be enough to get that one done. All right, so that's probably enough on these. These are all reasonably simple problems. I think I'll just stop this here and make a video on the problems that are a little less simple. Everybody have a great day.